today is Directional cohomology. So the question is, what is Directional cohomology and what's the use of this? Why do we care about Directional cohomology? So the idea of Directional cohomology grew from some research in some specific questions about mathematics, and the questions associated to the properties of functions on an arbitrary space that we will call a specific kind of arbitrary space that we will call manifold. So the functions on manifolds, the properties of functions on manifolds often depend on the topological properties of the manifold or the topological nature of the manifold. So it's important to know the topological nature of a manifold. And Directional cohomology is one of the tools that can help us to understand the topological nature of a manifold. So the first important thing, the questions associated to functions. Associated to properties of functions. So another question or something that stems from this prior question is how can we distinguish between two topological spaces? And can we classify all topological spaces that we know about? So this question is something even deeper. So can we distinguish between topological spaces? I might need a fresh marker.
Hasib, can you help us?
Thank you.
Okay.
So can we distinguish between topological spaces and can we classify all of them? So this is still an open question in mathematics. It's not yet resolved, but we have some ideas about some type of topological spaces. We can classify or distinguish some topological spaces, but we haven't yet been able to classify all the topological spaces that we know about. So to answer these questions, these are really deep questions and it's often difficult to answer. So to answer these questions, mathematicians approach the problem from many different ways. One of the ways or one of the things that comes from some prior researches of some prominent mathematicians is that we can define a group or an algebraic group that actually contains information about the topological nature of a manifold. So that algebraic group is one of the algebraic groups is Directional cohomology, and it comes from when we try to construct this group from a smooth manifold. So when we are dealing with smooth manifolds, we can construct an algebraic group that is called Directional cohomology that contains the information about the topological nature of that manifold. So, and to do that, we will use the notion of differential forms. So differential forms are used to construct this cohomology group. So in today's discussion, I will try to move from the very basic thing that is manifolds, and then move on to define tangent spaces and vector fields. Then we'll try to define differential forms, and then from that we will try to construct that cohomology group, Durham cohomology group, and from that we will try to identify if we can distinguish some of the topological spaces, or in our case, if we can distinguish some of the smooth manifolds. So, so this is our talk today, and I will try to cover all of the topics.
So, can I ask a question? Are we assuming anything about the compactness of the manifold?
Yes, we will consider the compactness as well.
Okay.
And if we eliminate that assumption, then the answer will change.
Okay.
So manifold. So what is manifold?
Why compactness is necessary?
So if I try to explain it very quickly,
He asked a question, why compactness is necessary?
why compact? No, it's not necessary. But I'm saying that the types of surfaces we will consider will be compact.
So compactness is not necessary.
Not necessary in general, yeah. So I will not probably show non-compact cases. So what is manifold anyway? So I'm going to very quickly describe what manifold is. So the prototype of a manifold, the thing that you can visualize when you consider or think about a manifold, is a surface. Okay, you can consider that it is in a 3-dimensional. So manifolds are topological spaces that are locally Euclidean. That means that is locally homeomorphic to some Rn. So that locally looks like an Euclidean space. So and then the other important thing is it has to be Hausdorff. That is, we need to be able to separate two distinct points of that manifold by two open sets, two disjoint open sets. That is the definition of Hausdorff spaces. And then it has to have a second countable, it has to have a countable basis as a topological space. So this is basically what is the formal definition of a manifold.
So what's a countable basis?
So the topological, as a topological space, it has to have a countable basis. So it has to have a basis that is countable.
I mean, I don't know the meaning of the word basis in this context.
Okay. So basis. Should I explain?
Okay, don't worry. It's
A collection of
Okay,
open
so
sets,
it's
countable
a-
open sets.
Okay, I
So
see, I see.
You take
Sure.
any open set and that can be written as a union of those.
Okay, okay.
So basis is a set of open sets that can generate all the other open sets.
Okay, yeah, I see.
So yeah, so this is what a manifold is, and whenever we think of manifold, we can think of some surfaces, or in general, all the graphs are manifolds.
I have a question. Why do you need Hausdorffness and second countability?
Oh, so it's because when we try to take limits, if our space is not Hausdorff, we cannot get unique limits, even if the sequence is convergent.
Okay, that's fine. So do you need the notion of limit if you want to decide on Durham homology here?
Probably not. I'll have to.
Right. So we don't need Hausdorffness here.
Yeah. But in the general formulation, basically, I mean, I've seen in most cases the Hausdorffness is assumed. Yeah, probably we
In
don't
this
need-
purpose, I don't think so. We don't need
probably
that.
Yeah. Okay, so graphs are always manifolds. So what do I mean by graph? So graph of a function f is the set so if f is a function from U that is a subset of some Rn and goes to some set Rm, the graph consists of all the points in the set in the space Rn plus m that whose first coordinate is the input value and the second coordinate is the output value.
Yeah, but I have a question. Where are these functions? These
So-
are functions on the manifold?
So if f is a function, yeah, so you can consider it as a manifold because I'm saying that
Yeah,
if
but you
f
are
is a
taking an open set from R to the n.
yeah, R to the n.
Yeah, but-
F is an open set from Rn and mapping to some subset of Rn.
I guess. I guess he meant whenever we have a function from two Euclidean spaces,
Yeah.
then its graph is a manifold. I think he's
Yeah,
right.
the graph gamma of f, it's a manifold.
That's what I'm guessing.
Okay. And where are these functions? These functions are functions on the manifold? They are not, right?
No, this function is just a function from Rn to Rm.
Okay.
Just-
That's what I was asking.
So if we have an arbitrary function that is, I will assume smoothness. So if it is a function from Rn to Rm, then its graph is a manifold. And in most cases, in our elementary vector calculus and everything, we see that our surfaces are parametrized, our curves are parametrized, so they are basically graphs. So yeah, this is a very broad example of what a manifold is. So the next notion that we will need is of,
What are some examples of manifolds? Those are not graph.
oh, okay. So there's the common discrete space that's a manifold, but that's not a graph. Should I? For our purpose, we can consider only graphs, or maybe the surfaces, or we can imagine surfaces or straight curves in case of manifolds. Okay, so basically we want to know about the tangent vectors and also tangent spaces. Okay, so basically our purpose is to develop an idea of a vector field. So the theory of differential form is like a more generalized version of vector calculus, and many of the questions that the theory of forms deal with stem from the vector calculus that we had before. So we need to have the notion of vectors. In general, if intuitively, if we have a surface, then at a point we can have a tangent plane. If we have a smooth surface, we can have a tangent plane, and any vector from the tangent space, from the tangent plane, is a tangent vector, right? So this is the basic idea. So if we have a point here, and if we have, we will have a different tangent plane, and at this point, on this plane, we can have a tangent vector. So in our normal sense, or what we know from R3, these tangent vectors are denoted with their usual coordinates. Say, if I think of this surface in a three-dimensional space, we can consider this to be a vector, or a concrete example would be something like this. And we may think that this point has some specific coordinate as well. So let's say this is a point P and this is a vector V. So V is this, and say point P, its coordinate is P1, P2, and P3. So the vector, in this case, the vector is this, but if we write it with the help of basis vectors, we could write it in this way, right? So where E1, E2, E3 are basis vectors. So, but we can actually generalize the idea of vectors to something useful. That is, we can turn vectors into operators that acts on functions, and it still conveys the idea of the coordinates and pointed arrows. So the way to do it is if we consider the unit vector along E1 as an operator that does the partial derivative in the x1 direction. Okay. Similarly, this. So, what's the helpful or usefulness of this? If you try to take directional derivatives of a function, you basically, when you do that, you basically take the dot product of this with v1, v2, v3. So when you take the dot product, you get v1 fx plus v2 fy plus v3 fz. So this is basically v1 del f del x1 x. Okay, I'm writing.
So what are V1, V2, and V3?
I
These are
should write
numbers.
x1, x2.
V1, V2, V3. These are numbers.
Yeah, these are numbers in this case. Yeah. So these are just the numbers, the coordinates of the vector at this in the tangent space. So the good part is, if we consider the vector as the operator, as this operator, we can just simply write this vector acted on this function to give out the directional derivative along that direction. So, and there is actually an isomorphism between these directional derivatives and the actual vectors, the pointed arrows. So, in our case, what we do is we consider vectors as directional derivatives, or this operator dv, and these are called derivations. And we will identify these two, and we will consider all the vectors as the derivations, because it gives us more flexibility to deal with functions and stuff. Okay, so that
I have a question. So you were defining this notion of derivation, and in that case you need inner product. Still you don't have the notion of tangent space. You don't have a vector space. But where do you find this inner product then?
Okay, so this is just the intuitive idea. So I'm just explaining the intuition behind it.
Okay.
We will formally define the derivations as tangent
Okay,
vectors.
so this sort of approach does not work in general. So
Yeah, this is intuition.
okay. So this is just true in Rn.
Yeah, the just true in R. So in general, the derivatives, or sorry, the tangent vectors. So tangent vectors at point P on a manifold M is defined as so it's a derivation that takes input of functions. Actually, it has a specific name. It's a germ of continuous functions, but we will not get into that. So the derivatives or the derivations take input of functions and give an output of a number. The directional derivatives. The numbers are the directional derivatives. So they have two properties. One, the D is linear, and it follows the Leibniz rule. So dfg equals df d of p plus f of p dt. So this is a derivation at a point, and we will call these derivations the tangent vectors. So these are our tangent vectors. And the set of all tangent vectors at a point, set of all tangent vectors, we will denote it by TPM. So tangent vectors, the tangent, and we will call it the tangent space at P. At P. So basically, this is the collection of all tangent vectors, of all the derivations of this form, and it is located at point P. And at different points, the tangent vector, the tangent spaces will be different. And actually, there's no overlapping between these because if you look at the intuitive diagram, the vectors here emanates from this point.
That means at each point you can define a tangent space.
Yeah. At each point of the manifold, there will be tangent spaces. So we have numerous tangent spaces at it. So, interesting thing is these tangent spaces, they don't have any overlapping because the vectors in this tangent space emanates from this point, and the vectors in this tangent space emanates from this point. So they don't have any overlapping in vectors.
How comes?
So if you think geometrically, then the tangent planes maybe have overlap, but they are not vectors. So these are not the vectors in the tangent spaces.
So that is the reason precisely one should not draw pictures.
Yeah.
That is really confusing.
Okay.
If I change the direction,
Pictures rather confused. Without this motivation, you could have started right from there. I suppose that.
Okay. All right. So
This is
my idea is, if we try to look at a circle and take the tangent spaces at every point, then so the vectors in this tangent space are these vectors, and the vectors in this tangent space are these vectors or this. So they don't match in a vectorial way. Two vectors are not
They
same.
have to be
parallel.
tangent.
They are not parallel.
They have to be tangent.
We won't think of them in R3. We just, they are totally distinct because, how can I say? So,
Yeah,
these,
maybe I got the idea because all the vectors should be tangent to that space.
yeah, tangent to some of it. We
Right.
can only compare the vectors between vectors in a single tangent space. We cannot just, if their origin is at different points, then we cannot compare the two vectors to be equal.
It's kind of an accident that they're intersecting in this picture. We have to think of all those two tangent spaces as separate. It's just an accident of our drawing that they're intersecting. There is no meaning to that.
It's a wrong picture. So think about, you have a circle and you have a line here, those lines are one-dimensional tangents.
Yeah, you can also, what Nilama said. So the tangent vectors could be in this direction as well. So in that case, there is no.
Yeah, but Milo, the question is how do you visualize it for the sphere case?
Our visualization is.
So tangent space is basically it's vectors of point-wise thing. So if you're changing point, then there is no way you can compare.
Yeah, my question is you asked us to draw that picture instead of the one that intersect each other, and then draw the picture of the one on the sphere.
You cannot visualize it.
Visualize that, right? So the picture thing is actually confusing. That's
So-
You cannot visualize.
The basic idea is the copies of tangent spaces are totally distinct and depends on the point. So it's like if we sometimes more precisely, the idea of the vectors are defined in a way that if it is from a space TPM, the tangent space at P, we denote, and it's a vector from this tangent space, we denote the vector in this manner,
That's the better
so
way.
that we don't have any.
That's right. That's how we do it. So another tangent space is Q, comma, some
Yeah,
other.
so
And
another tangent space will be, if W belongs to this, so this is, so they can never be equal because their first component.
they are disjoint. Obviously,
They are disjoint. So, so our goal is to compute. Our goal is to develop the idea of vector field. So, we have some intuitive idea about vector field that if we have a vector field on a surface. So what we want to do is we want to assign a vector at each point and assign a single vector at each point. So, and we will cover the whole manifold with the vectors.
So you mean that you're assigning a single vector at every tangent space?
Yeah, at every tangent space. So, so we need to formalize this idea, and for that, we will follow an approach that's called bundles, the tangent bundles, and sections. So tangent bundles are basically the collection of all, so this is the tangent bundle, this is the collection of all TPM. So what we're not doing is we are taking a big collection of all the tangent spaces together. So we now have all the tangent vectors on the manifold, not just a single point. So this is called, this is the, this is not really the tangent bundle. So tangent bundle is a structure that uses this space Tm and M, the manifold, and a projection map. Okay, and a projection map that is from Tm to M. So it defines, if you have if we have a point from this Tm, so it's an element of Tm is a ordered pair of point and a vector. It will give out the point, so it will specify which tangent space the element of Tm comes from. So this structure is called the tangent bundle, and in this tangent bundle so tangent bundle has all the tangent vectors from all the points. So we need to take single vectors from each of the points, and for that we will use the idea of section.
I have a question. So, the way you have introduced this tangent bundle, it looks like you are taking the base manifold or take a point of the base manifold,
This is
and
the
also
base
like and also the tangent vector and all the tangent vector. Right. So it looks like our Lagrangian mechanics is happening at this big Tm space, right? Because in the notion of manifold, there is no notion of Q dot, right? But in this Tm that you have defined, there is a notion of a point and the velocity vector. So is it true that our Lagrangian mechanics is so the Em is actually a manifold where our Lagrangian mechanics is taking place?
I'm not sure about that,
Right,
but
right.
Tm is also a
Because otherwise we do not have that
So
velocity.
the Hamiltonian that mechanics is happening in the cotangent one, and the Lagrangian mechanics is happening in the tangent one.
Okay, so the idea of section. So a section is a map that's opposite than the map projection. This is the projection map actually. So the section is a map from M to Tm. So it is a map that's assigning to every point of M an element from Tm. So it is, and it also have to, we can't assign 2 points at, two vectors at a point. So we need to have another property that is pi after x is the identity on M. And it also means that, when you are assigning with P some element from TPM, we are not assigning to P some element from TQM. So it ensures that this property. So this X, the section of the tangent bundle, and we will also assume that this X is smooth. And if that's the case, then X is called the vector field defined on the manifold. So this is the vector field. So vector fields are smooth sections of the tangent bundle.
So your Tm is also a manifold, right?
Tm is also, we can give Tm a manifold structure.
Yeah. You claim that your X is a smooth map. So it's a smooth map, smooth in the sense that it's a map between two manifolds.
Yeah,
right?
it's a map between two manifolds, and smooth in that sense.
I have a question. So you said that so at a certain point there may be like infinite tangent vectors, right? So is this map a kind of unique? Like you wrote that phi after x is identity map. So say it takes a point on the manifold and takes it to Tm,
Returns the point.
Tm returns back to M, right? I mean, is this a bijective sense, because which vector you are
So
taking,
there
right?
can be infinitely many vector fields. So you can choose infinitely many vectors, but not at the same time.
Point, there are like infinite many vectors,
Yeah,
right?
we are picking just one of them.
It's not necessarily that like a specific vector. It can be any vector.
Yeah, that can be possible. But for the smoothness condition to hold, we just cannot take just any vectors. So smoothness will specify some put some constraint on the assignment of vectors. The vectors need to vary smoothly if we are taking smooth vector field. Or if we don't incorporate the smoothness, then it can be any vector at those points. So it can be one in this direction, one in this. It doesn't need to be smooth if we don't apply the constraint of smoothness.
What I'm saying is that at a particular point, you can parameterize your vector by like different parameters, lambda, beta, whatever. The thing is that the vectors can be in different directions. So what your x is doing, it's taking a point or it's taking a vector from your tangent space, right?
It's taking a point from
taking a point
from the manifold
and
and assigning to that point a vector, and those vectors collection is Tn.
assigning
In a point, assigning in a point or with a point a vector.
a vector or the whole tangent space.
No,
Yeah,
a
a
vector
vector
in the
is
tangent space.
Just a single vector.
Just a single vector.
Just,
Yeah.
let me, so, sorry for the interruption.
No.
So this is your manifold.
Mhm.
Imagine this is one tangent space, another tangent space. This is the point P. So what Nafi is saying, if this is your point P, you cannot choose that vector. You have to choose a vector here.
Okay.
This is what Nafi is saying. If this is your point P, you cannot choose a vector here. You have to choose a point here. That is the second condition is
The
telling
second
you.
condition is telling you. So you get, if you apply the projection again, then you are not moving away. We will get the same point. Right? So yeah. So as you can see that if we go back to our basis representation, and this actually can be the basis of the tangent space if we employ the local coordinates. If we employ the local coordinates, we can write the basis of the tangent space, the collection of all these derivations, you can write them as a linear combination of derivations of this form. So if the local coordinates are this, so these are basically a way of, since all of the manifold is locally locally as homeomorphic to some Euclidean space, you can actually talk about their coordinates. And if you come from that coordinate system, you can think of some vectors that actually span all of the other vectors, all of the other derivations. So these are the this is the basis vector, and from here you can actually talk about the vector field. You know, if you don't write the point P, and if you don't specify the point, you can actually talk about a vector field that that is identical to this at every point. So these are our basis vectors, and anyways, the point of my saying that is,
Could you repeat your last sentence, what you said? Over here.
yeah. So we can have a vector field that will produce, if you specify the point, it will give out del x 1 at P.
Okay, then at all.
At every point.
But it's only defined in that coordinate patch.
Yeah.
So if you go to a different coordinate patch, there will be some transformations between them.
Then what do you mean by for all P in M?
So maybe I should not write this. Maybe I should just locally.
Yeah, that's
Yeah,
just
We should stay.
Yeah.
locally. So, but in Euclidean spaces,
it's
we
completely
can.
different in another neighborhood.
Yeah. So in Euclidean space, we can talk about. I want to give out an example of a vector field. Example of a vector field. So a vector field in R2 may look like this when you represent it with the help of the basis vectors. So it takes an input of point, and also it is an operator that can operate on a function. So and if you operate it or calculate the value of this, for a specific function, say x squared y, then you will get a concrete output value. So it will be like -2 y at this point plus.
So is your x an operator that takes C infinity n to itself?
It takes C infinity m to itself, yes.
Yeah, but you did not introduce that definition.
No, sir. So, there are multiple ways to define this tangent, this vector field. So the way I'm defining it from the smooth section of tangent bundle, but we could, bypass all this and we could define it from C infinity m to C infinity m.
So that is the definition that you are using now, right? As an operator.
So, sir, the thing is, when you take the tangent, when you take the smooth section of tangent bundle, it's also an element of TPM. So TPMs are derivations. So they operate on the.
They are point derivations.
They are point derivations. But when you take a vector field, yeah, if the point is not specified, it's the whole space.
Sorry, question. Over there, the derivation is a map from the C infinity to R. And you're saying that x is a derivation.
Yeah, x is a. And so this is, I should have said, this is a point derivation.
Exactly. Yeah, at a point. So it's better. What I do,
Oh, I see. Okay, yeah.
I DP whatever.
Right, right.
Yes,
I see.
I
Okay.
always attach a P with that D.
Okay.
So
yeah.
yeah.
Okay, I see. I see now.
That's a good
That's a
notation.
better thing.
Thank you.
Yeah. Okay.
Alright.
Is your x is the same as dz m to tm?
Yeah.
These two are same. Are you saying that?
And these x, x, y that you different, are these the same thing? Can you please explain how it's taking a point of in m and give an element in tm?
Okay, so I mean, I guess you are asking that if we have a R2, then what are the vectors and what are the points?
Right, so as you said, you take this point 1 to a point in the manifold m, and it should return an element of tm, right, which is the point m, point in the m and the vector, right?
Yeah, kind of. So we have that information with. I mean, are you saying that it should give out an information like this? Are you saying that it should produce something like this?
What I'm asking is that you see, like you define that x is a map from C infinity m to C infinity m, right? That's
Oh, okay.
one definition, but here you define another way that x is a map from m to tm.
Yeah.
So I'm trying to find like are they the same definition?
Oh, okay.
Can
So,
you explain?
so the thing is, this x is taking an input of C infinity m
Right,
function.
function is not m, right?
So, what is this taking? This is taking good of. Okay.
I'm asking, are these two definitions the same?
Yeah, they are same. They are
Can
same.
you please show?
They are same. And you can actually write, xp operates on f. You could write this, and this will give you the directional derivative of f
Right, at
Well,
point p. Right.
using this vector field.
Right.
And if you specify the point, it
Oh,
will.
it will give right.
Yeah, exactly. So this is will give the directional derivative. Yeah. So this will look like. And you can now try to compute this, and it will give out a specific number. And if we did not specify the point, it will give out a function. So that function is this is the output if we don't specify the point. Anyways, so this is our vector field, and we will need it. So we will go to another topic that's dual to this construction. I mean, that are dual to the vectors, and we call them differential forms. And actually, the Durand cohomology is defined in terms of differential forms. So the vectors. Okay, so basically, the idea of differential forms are, they came from the integrations in vector calculus. So, like when we have a line integral, we often, when we have a field that we want to integrate, F1, F2, we often integrate something of this form, right? So this is a form of a line integral. And sometimes we take surface integrals where, where we have dx, dy, and probably so parameters. Okay, so I'm writing very roughly. So you can imagine that, you know, when you have surface line integrals or surface integrals, the element we integrate are, you know, historically they were the source of the inspiration of differential forms. So the elements of this form that we integrate, I will write this more precisely later. Anyway, so the forms that we integrate actually are called the differential forms, but the idea of this was not very rigorous at first, and then mathematicians actually developed a rigorous way of defining the whole thing. So this is the idea of differential forms, or they will look like that. Okay, so the formal way of defining the differential forms. TPM is a vector field. Now, as a vector field, it has a dual space. So that dual space, vector. Sorry, I wrote the wrong thing. TPM is a tangent space. Tangent space. So as a vector field, vector space, this is a tangent space, and this is actually a vector space. It has a vector space structure. So as a vector space, it has a dual, and that dual, when we will denote it by TPS star m, it basically means that the dual of TPM, and it is called the covector space. And these covectors are called differential. If the covectors are smooth, we call them differential one forms. So differential one forms.
I think you are.
Oh, okay. So, sir, yeah, I did the wrong thing. Yeah. So we cannot just jump to defining them as differential forms. So we now have the covector space at a point at P.
Nafi, I have a question.
Yeah.
So far we know that TPM is it's a set. It contains bunch of vectors. So how do you know that it's a vector space? Is it trivial or you need a proof?
It's basically trivial because, you know, or very straightforward, you know, when you have
The way you are defining by germs then is trivial. Vector space structure is trivial.
when you define by terms, no, it's defined on an equivalence class, then we have to.
It's not trivial
It's
at
not
all.
trivial. But
So you should state that it's a theorem basically.
yeah, it's
It's a consequence of basically two different theorems.
yeah. So, but I bypassed the idea of terms, so we didn't define it as an equivalence class. Or I should have, but I skipped that part. So yeah. Anyways, so this is this has a vector space structure, and we can take the dual space. Okay, so the dual space has a, if the tangent space TPM has a basis that came from the local coordinates, we can take the dual of this basis and the dual basis will look like, will operate like, if you take an input of it will give out 1, but if you take a different vector in it, then say j that is different from 1, it will give out 0. So different from 1, it will give out 0. So basically this is the dual construction. So if it's this, and if you take an input of the z vector, you get the delta iz.
Question: why are you writing the dual as d of x? Because wouldn't it be more appropriate to write it as just x? Because your tangent vectors are in some coordinate system as d by dxi, right? Those are the basis tangent vectors.
Yeah.
So you're defining the cotangent vectors, the covectors as being dual, so that when the tangent vectors act on them, you get a delta function,
Yeah.
a Kronecker delta.
Yeah.
So wouldn't just using a simple-minded calculus rule, would it not be appropriate to write them as x of j rather than d of x of j?
So I think it's because we want to. The motivation came from the line integrals and the basic way of integrating things. And these were the basic look of differential forms. So probably that's
Okay.
why this notation is.
It's more of a notation, okay.
I have a question. I took GR class of physics some years ago, and he taught us that the TPM and the dual of TPM star, I mean the dual of covector, that's the V star star, is isomorphic to the original
The
space
original
V,
space,
right?
yeah.
So I mean like these relation, the dx take an input of the tangent vector and produce delta. Can it work oppositely?
Yeah,
I mean
it
like,
can
as
work oppositely.
the tangent vector, not on the covector eating the tangent vector, but the tangent vector can also eat the covectors and produce delta. Can it?
Yeah, if you consider the tensor algebra, then you can, we can do that.
I mean, is it only possible in only this
But
one form version? Can
In general, covectors can take an input of vectors, but but the thing is, here we will consider the one forms as functions from the tangent space. It's a linear function on the TPM.
Right, that I understand. I'm just saying that it can work in reverse, right? I mean, the tangent vectors can also take input covectors and put in the same delta, right?
Okay, so covectors can in general take inputs of vectors and give out the inner product. But
No, I
should
don't
we
know.
define it here?
I don't understand your question.
I don't understand the
So
question.
he's
the
saying
tangent
that,
vector
if you
is a
have
map from the function space to the set of real numbers. So how can that thing take input as the differential dxi? Is dxi a
Right,
function?
that's what my question is, because the V and V star star is isomorphic, right? So if you think that the V star is taking input from V, so V star star should take input from V, right?
What is
Uh, this is absolutely wrong. A vector and its double co-vector, they're not isomorphic. You cannot find these sort of things. As a vector space, these two things are isomorphic, and not in general. In some special case, like finite dimensional case. In that case,
I'm
you have
finding there who's saying
you have this sort of identification of the whole vector space. But point-wise, you cannot do that.
Yeah. So I can't think reverse, like in this sense that del x acts on dxi producing the same delta. I can't think like that.
You could say, del
for the
x,
sake
del
of-
x star star. Del
Oh.
xi star
Star,
star.
star.
That
Oh,
take
that
dxi.
yeah,
That's correct.
Okay.
Anyway, so let's move on. So this is a covector, or this is a covector that works in this way. This is the basis of the covector space, and from this we will define the differential one forms. So they are linear functionals. Linear functionals from TPM to R. So in the same way as we define in case of tangent space, in case of vector field, we can actually the forms are covector fields. So one forms are covector fields. So we will go about the same construction. That is, if we take the tangent bundle, we get the whole, the cotangent bundle, we get the whole space of all covectors. So, and then we can have a bundle structure on it with the projection map. So it will give out if alpha belongs to 2 star. So this is the bundle, and the section of this, the smooth section of this, will be called the one form. So one form is a smooth section of the tangent bundle. Identity map. Okay, so it's basically the same way as vector field work. So at every point we have a cotangent. We have a actually it's called cotangent space. So it's cotangent space. So at every point we have a cotangent space, and from there we will take one covector from each cotangent space. So and then if that selection is smooth, then we will call that a smooth covector field, and that is actually a one form. So alpha restricted at a point, when you consider alpha at a point, it's just a covector at that point. And it can take an input of a vector at point to give an output. So give a real number actually. So it belongs to a R. So, in general alpha, if you consider that, it's not just restricted to one point, if you consider the whole, if you omit the restriction of the point, then you can see that it can take an input of a vector field and will produce a function. Okay, because when the points vary, it will become a function. The outputs will become a function, and when you take an input, if the points vary, you are taking vectors at every point, so you are taking an input of a vector field. So you can think about the one forms in this way as well. So if you consider that, then alpha is a smooth map from the space of vector fields, smooth vector fields, to C infinity. So that's another way to characterize the one forms. Okay, so from
I have
here,
a question. So that alpha that net by m to c infinity m. Suppose in the c infinity m space, I have some algebraic structure. The functions we can define some sort of product. So I'm like for this map, can this structure be preserved? I'm like so, or
by alpha?
the algebraic structure can be induced in the map in this domain space that alpha of m or or it's just a real number mapping. There is no algebraic structure you are now using.
I'm not considering any algebraic structure on it, but the basic, this is a linear map. So
Yeah, that's what I was saying.
so these are, you can consider them as vector spaces. But apart from that,
I want to know the difference is just up to vector space mapping.
yeah. It's a linear map from a vector space to a vector space. So in general, one forms may look like this on a function on a manifold, that is, or in R3. So it may look like this. This is an example of a one form. So we have a function times one of the basis elements of the one form, and we have another function times this. So in general,
I think
this
you
is-
should be careful about it. What do you mean by basis elements?
So yeah, it will be
When you
this
are in the
movement.
companion space,
Yeah.
you can only mention
Yeah, we can
basis
mention
elements
this.
there.
Otherwise, I'll have to say it's a frame of the.
Sometimes there are sloppy languages like basis one form, but that does not make much sense.
Yes, sir. I'll try to avoid that.
I just used that kind of language in my tutorial the other day.
Okay, so so if we restrict it to some points, then we can have. It's possible to compute the values of the differential forms if you, if you plug in a point, and then if you plug in a vector, then you get a number. So,
Now, I have a big question. So with this third line alpha p, I guess you should tell we are evaluating alpha p at some given vector. Otherwise, you're gonna get a number.
yeah, we cannot get a number. We have to. This is still an operator on the vector space, on the tangent space. Anyway, so I will skip some of the parts and then move on to defining the other differential K forms. I mean, higher dimensional differential forms. So these are higher order differential forms. So these are this. So far, we just consider something of this form, but there are other differential forms that look like this. So let's try to develop them. When we have a collection of vector spaces, say V1, Vn, we can define a tensor algebra here by defining, if, so these are vector spaces. These are vector spaces, and we can define a tensor algebra on the product of the vector space. If we have a multiplication map so if we have a multiplication map, meaning that takes elements from this to another vector space Y, such that the basis of Y, so I should write basis of y is generated by the basis elements of the vector spaces v1, v2, v3, vn. So if xi belongs to vi, where vi's are the bases of the tensor, basis of vi.
So can I think of y as being the sum of all those vector spaces?
Sum of all. So we will consider it as a product, tensor product of all the v1, v dot, and vn.
So you're saying y is generated by all
The basis of y is generated by the basis elements of the. So this is a product map, tensor product map. It's taking an input of elements from vi's and then giving an output of another vector space y.
So he's saying that probably y is the tensor product of all those vector spaces.
Yeah.
So he is now forming a new vector space, y.
So what is the dimension of y?
So it will, as a tensor space, it will depend on the dimensions of this. So
This is the
here,
product
from
of-
here we can just so
Product
the
of the dimensions.
product of the dimensions.
I see.
But if we
Now I understand.
So, and we will write these elements as x1 tensor product, x2 tensor product, x3. So this is the way to write the basis elements of y.
It also evaluates at a particular point P of the manifold, right? This tensor.
This tensor is the general construction. This can happen at any
I mean,
collection
if
of
it is not, if it is over the whole manifold, then we call it for the tensor field.
No, he's just defining a tensor product on general vector spaces. He's not.
So this is a way to introduce exterior algebra.
At this point, it's at a particular point.
Yeah. So I'm trying to develop exterior algebra. So
Okay.
from here it's a tensor algebra, then I will go to exterior algebra. So the exterior algebra is, this is the way tensor product is defined. But
I'm not quite happy with the definition of tensor product. So is this map new given, or you are constructing such a map?
if mu is such a map that this condition holds, that this is a basis for y.
Yeah, but you have to impose some equivalence, there are some restrictions,
On mu.
So mu is not given, so you are constructing such a mu. If you can construct, then y is called blah.
Yeah, if there exists a mu such that this happens, then we can say that
Because in a general situation, for
we
example,
may not have that.
Yeah.
Yeah. If this exists, then we can call that it's a tensor.
Why would not it exist? I mean, these vector spaces are just like vanilla objects. It should always exist.
So think about, I define my mu
Yeah.
is a map, so every vector is mapped into 0. So then it goes to 0 basically. And
But he's defining that map over there. He's defining it as the product of all the bases. So, he's defining it in that way.
Defining the basis in
Yeah.
the y.
So, this map exists.
Do you think in the trivial case there will be a problem? Say, for example, there might be a basis, but it shouldn't be there. Is it?
yeah, so I cannot see it, why there should be such a map, why that is an obvious case.
Yeah. But if there exists, then we will call it the tensor product.
But Nafi, you're defining that map in the last line, right? And
No, I'm just right. It's a notation.
okay.
So
My
this a
concern
notation.
is with the existence first.
Yeah. So
Okay.
the notation we will use to to denote the basis element is this. We will write this instead of mu of this. So exterior algebra on a vector field, on a vector space V. Okay. So this is defined as we will have the usual so this is just we are denoting the tensor product by T naught by the T's. So it's the zero product, so it's just the trivial space. It's just the vector field if the vector space. It's just the field if the vector space is on the field F, then this is that F, and if T1V is the vector space V, and the TKV is the tensor product of. Okay, in this case, we will also say that Y is a tensor product of the vector spaces. So if TKV is the product of.
Nafi, I have a question. Yes, I think you are going very fast. So when you take this guy on the left side, for the mu map, okay. Suppose for the simplicity we just take two components, V1 and V2. Okay. So take the scalar alpha. Okay. And suppose I have a pair X and Y from V1 cross V2. So take that scalar and multiply it with that ordered pair X comma Y. And then it's an ordered pair. You close the bracket, right?
Yeah, of course.
And
I was thinking.
when you were thinking of X tensor Y, so it's going to be alpha X comma alpha Y, right?
Yeah.
But when your alpha is there in front of X tensor Y, is it going to be alpha X tensor alpha Y?
Okay. So the thing is.
No. Answer my question
Yeah.
first. So write it down. Alpha.
So you're saying that mu of alpha is.
No. Forget about.
Is it?
No. Erase everything. So you put alpha in front of. Just write alpha,
Okay.
and inside bracket. Complete the bracket. Inside bracket is X tensor Y.
Oh, okay.
What is that? How do you distribute alpha?
Oh, we don't. It can be this, or it can be this.
Yeah.
But on the left side, when you write alpha is multiplied with X comma Y. No. In the very first line.
Oh, okay.
No, not here.
No.
Here.
Yeah. What is that? This is alpha X comma alpha Y.
Yeah. I'm not sure what are you referring to. I mean,
I'm
if
referring
you're-
that.
But
when
that's
you
not
are-
that's not a tensor product.
So xy is a vector from V1 cross V2.
Yeah, it's a vector from D1
Yeah,
cross
but
D2.
when you were defining this map, you should have clarified these points.
Oh,
That you need some, you have to declare an equivalence relation that needs to be obeyed. A bunch of relations.
That's what I said. The construction is not obvious. So you need to identify by some sort of ideal. Then you have.
Right, exactly. That's the whole construction. So you could have briefly told about these
So it's not
constructions.
obvious at all.
It's not complete. That's what Milan was referring to earlier.
So, I mean, the whole exposure here will not be complete. I will really give out holes because I'm not sure if I can cover everything.
I don't know, it's a bit obvious. Can also there is something
What is obvious?
like oh, just
Yeah, because
wide
your
spaces.
face is, that's why it's obvious to you. And your face is, that's why it's obvious to you, because you're familiar with that construction from
Yes.
quantum mechanics, that's
Yes.
why.
I just
But
gave
he's
an-
not, so,
I
yeah.
just gave an example that alpha x comma y is not the same as
Yeah,
alpha
exactly,
x
yeah,
tensor
yeah.
y. Now,
No.
is it obvious to you?
Yeah, but he's not defining it in this way. He's just constructing the basis in the y space. I really don't see where's
No, it was also obvious to me, because I was thinking of quantum mechanics and tensor
Yeah,
power.
there-
you guys
there are-
raised the
yeah.
flag. That's
So,
all.
so I filled in the
There are
gap by
subtleties.
myself, you know, so they didn't, that's the
The
point,
thing
so,
is,
yeah.
when in mathematics, whenever you want to define some concept, you have to be very careful if the definition actually works
Yeah.
or not.
That's people are naive.
So life on the right hand side,
Okay, yeah.
you have to explain what the life is there on the other side.
Yeah.
It's not conveyed completely in this definition, how the life is there. So we are all familiar with the life on the left hand side, right? That's just a Cartesian product of vector spaces.
Yeah.
But what is the life there?
Hmm.
Milon is asking about that.
Yes, that's right. So, yeah.
Is there.
Um, So in this case, we will try to define an equivalence relation on the space TKV. For any k, we will try to form an equivalence relation. This that says that if in this product, in product of two, okay, let's write it in a different way. So let's define a set AKV, that is the span of all such for which xi equals xj for some ij. Okay. Then if we mod out and we will denote this as the exterior kth exterior power, so it's the kth exterior power. Okay. So the kth exterior power of V. So if we take the quotient space of TKV by AKV, we get the kth exterior power of the vector space V. So here what happens is, if we have in the space AKV, we have all those elements for which some of the basis vectors from if this is an element in here, in some case xi or equal to xj for some I and j. So basically, if we mod out by this AKV, we will get all those elements from here, or the equivalence class of all those elements, for which no no element or no basis element is repeated. No basis element of, you know, the vector space V is repeated in the basis of the kth exterior powers, the set of the kth exterior power. So, and this space is the elements of this space. I mean, have a product, a natural product. So I should say that we can have a collection of.
Now, if you ask a big question, how do you capture the notion of anti-symmetry? For example, V1 weighs V2
Okay.
equals to negative V2 weighs V2 from this construction.
Okay, so it comes from, if I just write, show you for this. So X plus Ey. X plus Ey. So then you can write it as, so this is actually 0, right? When you I should say that,
If you take tensor product, that
Yeah.
will be 0 by your construct.
yeah, so this is actually the class of 0. So the class of this is 0.
Yeah, that's yeah, good job.
So, and if you multiply this,
Yeah.
then you get.
Thanks.
And we also repeat that dx cross dx is 0.
Yeah.
So
And dy is 0. So then become.
Thanks.
So yeah, so the properties. Okay, we
I
will.
have a comment on that. So I think physically you can think of the dx dy, only it is capturing the area of some elements. It has an orientation.
Well, you were not saying this thing in this definition. That you were not saying that thing in this definition.
Okay, so the thing I was going to define next is when we have these spaces, we can have a natural map from two of them. Say you take okay, so kth exterior power, lth exterior power. You can define a map on the cross product of them to an element of k plus l exterior power. So that map is called wedge. So this is the wedge product. So that's the wedge product, and this is actually very naturally given. Okay, so I was yeah, I wrote this. Yeah. So the elements of the kth exterior power are of this form. So it's if you take the kth exterior, an element from the kth exterior power, it's like this. And if you take an element from the lth exterior power, it's this. And if you apply wedge on them, you can get an output from here very naturally. If you take the so, and this is actually well defined. So, yeah.
your L looks like 1. Your L looks like 1.
Okay, L looks like 1.
The-
Okay. So, oh, this L also.
I don't think you're writing it better than mine.
It's hard to write on blackboards. I didn't know that. No,
So it's graded out.
yeah. So I was saying that when we have when we take all of them, we can define this actually it goes on until it's 0. So this is, if you consider the whole collection of the exterior powers, then this wedge product actually gives a map, it gives an operation on this. So this is called the graded algebra. This forms the exterior algebra on the, the pair is called the exterior algebra. Okay. So the point is, if we take, so whatever we define so far, we will apply it to the vector space of the vector space of differential one forms. So if we do that, we can actually define from this. If we define the exterior algebra on that vector space, we get the collection of all differential forms.
Acha, Nafi, I was just going to suggest, what if we continue the seminar next Thursday?
Yes.
Because that way,
Okay.
people can go home for iftar in time.
You don't have to hurry.
And you don't have to hurry. And this is, for me, it's extremely interesting and fascinating. I'm learning stuff that I thought I knew, about a subject that I thought I knew. So, what do you think about that suggestion?
Yeah, I think that's a good idea.
Okay. So, is this, when is a good point for us to stop there?
We can stop here, or we can just apply the, we can define the differential K forms, and then maybe I will take 5 more minutes.
Okay,
And then we
sure.
can stop.
Yeah, and then we can.
Alright. Okay. So this is the exterior algebra, and then so if we take the vector space of the covectors or differential one forms, so if we do that, we get the actually this is, in this we have a decomposition of this form. Okay, so elements of this will be called, we can define omega star m to be the collection of all the direct sum of all of the elements that we get from the exterior algebra. So these are any element from omega star m will be called is a differential form.
Sorry, what is omega 1m? I don't think I've seen this.
So omega 1m is the set of all differential one forms
But is that a vector space?
On a manifold or?
on a manifold.
Yeah. Because there's an m there, right?
Yeah.
So you're extending the local construction to a more global construction.
No, basically we are trying to define higher order forms from the one forms.
That's right, but on the left hand side, that's a vector space.
Yeah, so that's a vector space, and we have that vector space as omega 1m, the set of all differential forms.
Yeah.
So the set of all differential forms on M, it's a vector space.
Is omega 1 or omega L form? Is omega 1 or omega L?
One.
So
Omega 1.
this is omega 1m. This vector space is used to generate all the other higher order powers.
What is omega 2? It's like dx wedge dy.
Yeah, kind of.
What is the vector space structure there?
Yes.
Is the, I understand that you said that the cotangent spaces are vector spaces. Now you're
So-
talking about one form.
No. I mistakenly said that maybe. So the underlying vector space in this case is not just the cotangent spaces. It's the set of differential one forms.
So it has a model structure.
So when we have the set of differential one forms,
Yeah. How is that a vector space?
so
Is it a vector space?
check it. Let's see.
The space of all one forms on the manifold.
At every point on the manifold, it's a vector space.
Yeah. But when you're taking differential one forms, do they constitute a vector space?
I think so.
It has a vector space right now, but has also a model structure because all these one forms is C infinity.
Yeah, it's a C infinity M module that I know, but how?
Oh, okay.
It's also a vector space.
Are vector space?
I mean, sir, is there any way, is there anything that says that, any idea that says that it's not a vector space?
No, you do. So it's a C infinity module, and also it has an R vector space.
What's a hard vector space?
It's a vector space over the field of
Vector
vector
space over the field of fields.
So, if omega, since omega is an element from the larger omega, so it is, and this is a direct sum of this. So omega. Sorry, I shouldn't say that. So it's if omega belongs to km, omega km, then we say that omega is a differential k form. So this is a differential k form, and we will talk about maybe since we are having another class, we will talk about the geometric interpretations, or what do they do in general, the differential k forms in the next session, and develop the idea of the I think we can.
Thank you very much. Yeah.
Very much.
Thank you.